that this would happen.
I can only see one of the, oh yeah, wow. There's a lot of people.
There's 34 now.
Yeah.
Well, we are going to just wait for a minute or so, just to make sure we have a stable number of participants.
It looks like about half of people are logged in. And
so we have a bet going on, right? Alex said 55 people. So if it is 55, she wins. Below 55, we win. It's 37 right now. Go, go, go. All right, I'm looking through. We have a lot of students from United States. Welcome, everybody. This is Rahmi Özışık. I'm one of the professors in the Material Science and Engineering department. My colleague, Ed Palermo. Hi, Ed. And then we have another colleague from RPI, Alexandria Pizzola, who is a assistant, was it assistant director?
Assistant Director of Admissions, yes.
Admissions. So if you have any admissions-related questions, she's going to answer those questions. I think we are stable. We are at 38. So we are going to start. We are very happy that you are considering RPI, first of all, as a school, and Material Science and Engineering as a major, as a possible major. RPI offers multiple majors, obviously. We have 5 schools, and out of this, School of Engineering is the biggest one. First, let's look at where RPI is. RPI is located in Troy, New York. We are approximately 150 miles from New York City, to the north of New York City, 180 miles to the west of Boston, and about 220 miles to the south of Montreal. We are central New York. We are very close to the capital of New York, Albany. Actually, there are 3 big cities where we live: Troy, Albany, and Schenectady. So then this region is called the capital region. You see a few things. One, the picture on the top right is one of our centers. And the picture on the bottom right is actually what we have around. We have 40-something peaks. So if you are one of those students who are outdoorsy and wants to hike, like one of my sons, there's going to be a lot of challenge for you. People in this region hike all these mountains, and then they hike them again during the winter. So they keep track of how many they hike during the good weather, summer, and maybe in the winter. So just a quick info. Next one, I have a question to, no, that's okay. So RPI was founded in 1824. It is one of the oldest technological research universities. Actually, RPI is the first university in the Western Hemisphere that offered an engineering degree. That was civil engineering. And civil meant at the time, not it means today. Civil today means just construction, but civil at the time meant civil being not military. Okay. School of Engineering is the largest school within RPI. There are 5 schools: Architecture, Management, School of Science, School of Engineering, and School of, what am I missing? Humanities and Social Sciences. Yes. RPI has been known and is still known with it as engineering school. This is about what our strength is. We have many centers, research activities. We are one of the top 50 universities in the United States. School of Engineering has 7 departments, but some departments offer more than one major. So, for example, mechanical engineering, nuclear engineering, and aeronautical engineering are all under the one department umbrella, but they offer 3 different, at least 3, maybe more majors or degrees. In our department, we have approximately 15 faculty. Numbers sometimes slightly change, but here is a list of faculty. I ordered them in the alphabetically with last name. Hopefully, I didn't make a mistake. Our department head is Pavel Kablinski. We have many different backgrounds, actually. Some of are physicists, some of us are material science and engineering majors. Ed and I are actually undergraduate degrees in mechanical engineering. Ed went on to do things in biology, materials interface. I went to do things in polymers and polymeric materials. Some of us do research on glasses, ceramics, amorphous materials, semiconducting materials, energetic materials, metals, metallurgy, nanostructures, nanocomposites, and so forth. We are a small department compared to many other majors at RPI, at the School of Engineering. Our undergraduate student population per year ranges from 20 to 30, generally does not exceed 30, and generally is above 20, but it does fluctuate based on the year. So in total, maybe we have, I don't know, 80 something students over the 4 years. And this gives us an advantage in the sense that we all know our students, unless of course they are specifically hiding from us, which is not really that possible, to be honest. And they know us very well. I have, and I'm sure Ed can speak on this too, I am one of the advisors in our department. We have 4 undergraduate advisors. I will actually be the advisor to the incoming freshman class. And I will, for example, take that incoming freshman class all through 4 years, and I will help them graduate, or I'll make sure that they have fulfilled all the graduation degree requirements. In other departments, this might be done by professional staff, partially by professional staff and partially by faculty. In School of Engineering, we have a new advising architecture or structure, let's say. The first year especially, the students in the first year, they are advised by what we call engineering hub. So this is a group of staff members. Their only job is to advise students. So if you have a problem with course selection, a course, right? You are having problems with a course. You don't know what to register the following semester. You want to drop something. You don't know how to drop it. You want to add a course. You don't know how to add a course. Anything that comes up, engineering hub staff is there all day, every day to help students. But of course, they do not necessarily have all the information into the department. And so I will, or somebody like me from the department, in our case, a faculty member from Material Science and Engineering, will be also assigned to that group of students, to that cohort. And when necessary, we'll step in. We will help resolve issues and conflicts and so forth. Let's touch briefly on what kind of research that takes place. Our department, Material Science and Engineering, as I mentioned, we don't have a lot of undergraduate students. So our department strength actually is the amount of research we do. If you think of RPI as a business, and RPI is not really a business, it's an educational institution. We care about our students, not the money that they bring in. But if you think of it as a business, you, of course, appreciate that each unit within RPI should kind of carry its own weight. And we do. So we might not have a lot of students, but we have a lot of research expenditures. We bring in a lot of money, and RPI takes a cut out of this research. And that's how we keep the buildings running, electricity in the labs, and we need to buy equipment that might be too expensive, that's how RPI helps us accomplish these things. So your tuition doesn't only give you an undergraduate degree, but it gives you many other opportunities like research. And in the last maybe 10 years or so, we have seen a lot of interest from undergraduate students, and especially from students like you who are still in high school. They are looking to pick a university, but they are interested. Somehow they have already picked some fields, or they have some interest in materials or certain materials. They have learned things in chemistry or physics that they think that maybe materials is their chosen path. So we, as a department, are able to offer a lot of undergraduate research experiences to students. Last year, I had an average of, I think, 6 or 7 undergraduate students working with me per semester. This summer, even though the school is off, I have 3 of our undergraduates and 1 undergraduate student from another university working for me. And the labs are closed, unfortunately, but they can still do theoretical work. I teach them certain things, and I ask them, I kind of give them homeworks. They go do it, or read papers. They summarize them. They make presentations for me. So these are the things that we can still offer, even though the school is closed right now. But hopefully, if Alex can correct me, RPI is planning to open up in the fall, and the freshmen will be allowed back. So, and hopefully we'll open the labs, we'll open the classrooms and so forth, and we'll be able to have hopefully close to a normal education setting. The 4 gentlemen you see on the right column here used to be assistant professors. They are not anymore, as far as I know. But those are the recent hires we had in our department. Our research goes through all kinds of things. Some of our faculty have actually spun off companies from their research. So there are a lot of examples of wide research activities taking place. Here is a picture of our recent graduates. The bottom picture is the undergraduate students graduating. This is from our material science and engineering graduation dinner. And the top picture is actually our graduate students, those who have received a doctoral degree. We have, I can tell you, we have around, depending on the year again, 40 to 60 graduate students in addition to undergraduates. So we have kind of like an equal amount of undergraduates and graduates in our department. Many of the research is supported by companies, but also many of our alumni work at these companies. So we are able to keep, we actually within the department keep track of where our students do their internships, their co-ops, or maybe they go have jobs at these companies, and we reach out to them, or sometimes, mostly, for example, just last week, one of my recent graduates reached out to me, and his company is looking for co-op students who would be interested in co-ops and internships, and or sometimes jobs. So this is how we internally handle it. But RPI also has a different department, an office that handles or tries to arrange internships and co-ops to students and helps them with their resume, preparing their resumes, maybe preparing for interviews and so forth. So that's also available to RPI students. This is just a very small list that we put together. There are, of course, many, many other companies that our students have done internships, co-ops, and research, and or have jobs at. I didn't have my chat on. I was on the participants list. Are there any questions that we should answer? If I try to read all of these now, I think I'm gonna. Alex, would you like to just step in and tell me if there are any questions that I should?
Absolutely. Elijah asked, are there any material science and engineering courses that are geared toward nanotechnology or nanoscience? Okay.
There is one course specifically that has nano in the title of the course. This initially was a graduate level course, but now it is also an undergraduate level course. So it has both graduate and undergraduate students. Of course, the expectations from graduate students and the undergraduates are slightly different, right? You are not competing with graduate students for grade. But we have nano or nanoscience, nanoengineering in many other courses, even though that might not be in the name. in our department, we have required courses that try to teach you what is material science and engineering, right? What is, and maybe this is a good opportunity. Material science and engineering is all about understanding the atomistic scale structure, molecular level structure of materials. Is there an organization to atoms? Is there no organization? The structure at the atomistic scale influences macro scale structure, which then influences the properties of the materials. But if you process a material, you would change its structure. That will change its properties. Therefore, the whole curriculum is laid around trying to teach students what is structure, how do you characterize structure, how do properties relate to structure, and what happens when you process something, what happens to the structure, and that way, then you can maybe understand what happens to the properties, right? What are the parameters you might want to control, for example, during processing to achieve a certain set of properties in a given material, right? So these are the things that we teach. But outside this main curriculum, these are required courses. We also have elective courses. Each of our undergraduate students must take at least 2 elective materials courses. And in these courses, for example, I and Ed currently has been teaching Introduction to Polymers. We have courses in energetic materials, materials under extreme pressure, metallurgy, glass science. All these concepts of nanoscale science and engineering are built into these courses. So we cannot avoid not talking about nanoscale, because if we are talking about structure at the atomistic scale, that's really what we are focusing on, right? Structure at the nanoscale. And a lot of our research, if not all, to be honest, is on nanoscale science and engineering. Somehow we are, the grants, the funds that we receive are mostly on this field, and therefore that kind of seeps into our educational curriculum too. I talk too much. I am hoping I'm not talking too much, but Ed, please chip in if you have anything.
No, I would say that almost all of our research is somehow related to the nanoscale. And yes, we have one course that's specifically called nanotechnology, but almost every course, the nanoscale is really important part of this structure property relationship phenomena. So yeah, here Rami's showing a slide with a few example images of different nanomaterials that various people in our department work with.
In almost all of these slides, there's a bunch of slides here. I'm highlighting certain research. Is the voice okay?
Yeah, I can hear.
Okay, all right. For example, here is a short list of research topics, let's say, and then the faculty members that are interested or involved in that kind of research. And then the following slides are all about research done by different faculty, highlighting certain aspects of their research. But the common theme, if you look at these, the common theme of all of these slides is going to be, you are going to see structures, materials at the sub-micron scale, at the nanoscale, right? Here is some examples on nanostructured materials. Here are some examples on, I think this is, what is this? Is this a copolymer?
That is Chaitanya's work, and part of it in collaboration with myself. So this is super resolution optical microscopy. So he's able to see nanoscale features in a material at finer length scales than a typical optical microscope would be able to do, using some very fancy optics. So yeah, you have a block copolymer layer on the bottom right there. The top is actually a self-assembled monolayer of a type of material called photochromic switch. And then on the left, these are little polymer beads that were self-assembled into some object called a superlattice.
For example, here, and this is also Ed's research. So Ed, go ahead.
Okay, just 1 second. There's a question from Alec that says, are there any courses related to manufacturing? And the answer is yes. We have a course specifically called synthesis and processing, which is all about how the various classes of materials get made, processed from raw material into the actual useful engineering object. I hope that answers your question.
I can chip in here because the student is asking also 3D printing.
Yep.
RPI has a standalone lab. It's called the Forge that has 3D printing equipment. It's open. It's controlled by students. It is open to all students. You just have to be, I assume you have to be trained to use things. And but any student who is interested in 3D printing can actually go and experiment, make 3D prints, make useful stuff.
And if I could just chip into that as well, that facility is currently being used to make personal protective equipment, and we donate it to various hospitals in the region, like a face shield, for example, being 3D printed on campus since the COVID started.
That's a perfect example of
useful.
I guess how we could do useful things sometimes. Go ahead, Ed. This is your research. Tell us. This is very interesting, actually. I like this.
For this slide, there's a couple different things going on here, and it's actually also part of it is COVID related. So we've worked, my lab since the beginning, and since I was in graduate school, we've been interested in antimicrobial materials. And traditionally, that's been more focused on antibiotic drug-resistant bacteria. But these days, we're working on antiviral versions of such materials. So these are polymers that can kill microorganisms on contact. And so we've developed, and we have an NSF-funded proposal on coating N95 mask materials with this antiviral polymer material. So a typical face mask just filters out the virus so it doesn't get in, but the virus is still sort of live on the outside of it. These materials inactivate or deactivate the virus when the respiratory droplet hits the material. And so we're developing assays to prove that these materials are effective at killing coronavirus. At RPI, we have enough biosafety level facilities to test against model coronaviruses, and we're collaborating with medical doctors at Mount Sinai who have a higher level of security clearance, if you will, in the biosafety world. And they're testing these materials against the actual SARS-CoV-2, the virus that's causing the current pandemic. Then also shown here is some electrospun fibers that are made out of something called a polypro drug. So here for application in spinal cord injury, we have a polymer that's actually made out of a drug. So a polymer is a long chain molecule of repeating units. Here, the repeating unit in the polymer is a drug molecule. So then in the body, this material is broken down, it's hydrolyzed, it's degraded chemically, and the drug comes out slowly. So we build tissue engineering scaffolds out of the polypro drug, and that tells the cells within the tissue what to do. And specifically, it encourages neurons to grow in the direction of these electrospun fibers, as shown in the upper right-hand electron microscopy image. So that's one of a new collaboration that I have going on with biomedical engineers here at RPI, and also shows our research in all departments and even across schools is very highly collaborative. So if you join a research lab and work on something materials related, there's a very high chance that you'll also be connected to some other discipline, whether it be biology, biomedical, it could be mechanical engineering, manufacturing, and so on and so forth. So it's a very small and tight-knit research community here at RPI.
All right, here's another example. This is on glasses and amorphous materials. Obviously, you are well aware this changed since the introduction of the iPhone. Every time we talk about glass now, the example always turns out to be an iPhone glass. Corning is mainly responsible for many of the developments in this Gorilla Glass, and many of our students, undergraduate and graduate doctoral students, work at the Corning research labs, focusing on certain aspects of this. We have one of the leading scientists in the world in our department own glasses, and now he's not alone, actually. Now there are additions to his research area. Basically, 3 faculty members mainly. They work with Corning. Their graduates almost always end up at Corning, and they are interested in how can we make glass not brittle, more ductile. Unfortunately, ductile is an engineering word, but we don't want it to break easily. You want it to not break only, let's say, upon bending, but also upon impact, right? I am just seeing a question right now. Oh, and Alexander, they already answered this, but Learning Center. Yes, we do have a, so one student asked, what are the different areas of engineering study at Rensselaer? I will maybe take on that part. We said there are 7 departments. I'll try to list all the majors that I know. And Alex, if I miss anything, please. So material science and engineering, the most important one.
One,
And the best.
10 more.
Not very, very, very wide range, but the second one might be any one of the other ones. I'm just going to mention a few. So mechanical engineering, civil engineering, electrical engineering, computer science and computer science and computer systems engineering, industrial engineering, which we call decision sciences. I believe we call decision sciences at RPI. I fail to remember the whole name now. Aeronautical engineering, nuclear engineering, biomedical engineering, chemical engineering. Did I count civil? I think I did. What else?
Did you say environmental?
I did not say environmental. Okay.
Okay, that was the last one then.
Okay, that's good. Then that's
good.
All we have. So those are all the different majors in the School of Engineering. All right. Here is a snapshot of some metallurgical research going on. Here is some energetic materials. Again, just pay attention to the fact that I'm showing you a lot of pictures that relate to the structure of materials. This is the bread and butter of our of material science and engineering. How do you process materials to get this structure, for example, on the left, versus the structure on the right? Alex, do the students see my mouse pointer? No. Okay. So I need to verbally state it. So on the left, you see 4 pictures at 450, 650, 750, and 850 degrees centigrade, how the structure is kind of evolving. But if you imagine, forget the temperatures right now, but if you imagine you have the upper left structure, which looks bland, and then the lower right structure, which maybe has a lot of creases and other things in it, the properties of those structures will be different. And this is what material science engineers try to do. Understand the structure through optical microscopy, electron microscopy, such as scanning electron microscopy or transmission electron microscopy, atomic force microscopy, using these techniques to understand the structure, to visualize the structure, but then do testing, all kinds of testing, rheological, viscoelastic, mechanical, electrical, optical, thermal testing to understand the properties and how these properties change as a result of the change in structure and or composition, of course. Here is some examples from electronic materials. I don't know the details of this research. Ed, do you know anything about this? This is partially Shankar's work, I think.
Yeah, some of it is Shankar's, some of it is Daniel Gall. So he's a professor that looks experimentally and theoretically at the electronic structure of metal interconnects within devices that are like part of electronics. And in the upper right is Jian Shi's work. He looks at complex oxide materials. These are a kind of ceramic, and particularly he really wants to know how to control their crystallization, again, for some energy related application. He looks at perovskites, which are a very popular type of material for photovoltaics, for example.
Okay, thank you. We are a very interesting department. We have quite a lot of faculty members who, as part of their research, they also use computational methods to study materials, material structure, and materials properties. I'm one of them. My graduate students are split between doing hands-on experimental research, and then once in a while, I get a student who has the courage to maybe take on some computational work, do simulations, and so forth. Here are some results from simulations. The one on the bottom right, actually, it's not clear, but this is a nano-indentation experiment on a group, on a surface, on a material. This wedge that you see actually is created by a tip pushing into the material, right? And then on the top right, you see different structures of glasses, probably having different compositions. And that's what the percentages are indicating, at least, and how the certain properties of them change. All of this is done. This is not result of experimental imaging. This is computational study and prediction of the materials properties through simulations. Here are some other research. This one, I think, I don't know the Hull's research that much. Ed, do you know? I think you are aware of Shankar's.
Robert Hull, stuff on the top. Oh yeah, Microstructure Evolution. They are looking at, I don't remember exactly what kind of material it is, but trying to understand how to control structure as it evolves during processing. And then on the bottom half, Shankar is working on using AI and machine learning to correlate processing parameters with the performance of polymers. And we have a question about the coursework. I'm going to send a link to our advising booklet for undergraduates. And on page, if you give me 1 second, page 10, you'll see the template for all of the courses that materials engineers take. So page 10 of our advising booklet.
I can verbally state a few things about the coursework. Generally speaking, students take 4 to 5 courses per semester. Generally speaking, again, 4 of these are probably 4-credit courses. So it's 16 credits. And then the 5th course, of course, could be a 4-credit course or 3-credit course, but generally it is a 1-credit course. Every engineering student has room for at least 2 1-credit courses. Then the only 1-credit courses that RPI has or School of Engineering has are introductory courses. For example, Material Science and Engineering department has a course called Introduction to Material Science. It's a first-year 1-credit course. There's no exams on it. I believe you write maybe 2 writing assignments, 1 page each, approximately. The main goal is here faculty members come and talk to you about their research, about their interests. You go visit labs. You learn, for example, the tools, the equipment we have in the lab at RPI and what we do with it. So you get a glimpse of what do material science and engineers do and what kind of labs we have, what equipment we use, and so forth. I believe nuclear engineering has a course like this. So if you are interested in a major, but you have not made your decision yet, these 1-credit courses are pretty useful for you, would be useful to you in trying to choose a major. So the first year is mostly math, physics, chemistry. Actually, the first 3 semesters is math, physics, and chemistry. In our department, our students take the first materials course. In the first year, it's a course called a 4-credit course called Material Science. It has some lab component to it. It's generally a spring level course, because I would think that students take the 1-credit Introduction to Materials Engineering course the first semester, and then Material Science course the second semester. And then the second year, of course, we get into a little bit more into materials. The third year is generally, we have more materials courses than other courses. And then the fourth year culminates in whatever, one materials course each semester, some maybe materials electives, and a capstone experience. Every engineering student has to do a capstone experience, basically a project course before they graduate, and that happens in the senior year.
I would also add to that, many students come in with AP credit. So a lot of the basic science and math courses are sometimes already taken care of through AP. And if that's the case, I've known of some examples of students who completed the bachelor's degree in less than the 8 semesters. And we also have what's called a coterminal master's program, where you can, after you finish the bachelor's, you can stay at RPI for an extra year or 2 semesters and earn a master's degree as well as a bachelor's. And a lot of our top students elect to do so because normally a master's degree takes 2 years if you go to a different school. Robert is asking about internships. Yes, we have many co-op and internship opportunities that students will do in the fall or spring semester of the junior year.
Yeah, but we do not have, I think RIT has a more strict co-op requirement. I believe we don't. Alex, yes, please.
Yeah, absolutely. So at Rensselaer, it's a little bit different from what you're talking about if you're asking about like a specific co-op placement program. So RIT has a specific built into their engineering curriculum. They have an entire year of co-op where they actually place you in a co-op. You spend your year there. At Rensselaer, it's a little bit different. It's a little bit more flexible. Our engineering curriculum is 4 years, and within those 4 years, you have opportunities to do things like co-ops or internships or even research. It really depends on what you're interested in. So it's not always co-ops. It's not always internships. Students do that through a program at Rensselaer called the Arch, which shifts our academic calendar so that our juniors actually pre-complete half of their junior year in the summer before their traditional junior year, and then spend 1 semester of their junior year away doing something like a co-op or an internship or research. Again, it's a little bit more flexible and not a full like traditional co-op program, to allow you a little bit more choice when it comes to what you actually want to do. Our students typically find that they like that because they're pretty self-determined students.
Yes. All right, perfect. What else can we talk about? Because these are the slides that I have here basically are all research now, but I see more questions are more about practical things about RPI. So if we can open maybe the floor to more questions. I don't know that I have anything else to say about specifically about material science and engineering, unless Ed has something in mind.
No, I think you nailed it.
All right. Thank you. I will add something. Ed mentioned this coterminal program. I've had many students in the past who came in with quite a lot of AP credits, and then they were able to finish both their undergraduate degree and the coterminal program, the master's degree, in 4 years. In regards to interns and co-op, if you do a co-op generally is a summer semester and a academic year semester. For example, spring and summer, or summer and fall. If you do this, you might think, oh well, I'm losing a semester of school, but it doesn't work like that. With the Arch program, actually, because we take one of your summers away from you, the summer after the sophomore year, you are still graduating on time within the exact 4 years. So that should not be a worry. Maybe one other practical thing. I believe, Alex can correct me, I believe students can register up to 21 credits of coursework per semester. And that is included in your tuition.
Oh, hang on. I lost you,
Yes.
Rami.
Oh. Am I back now?
Yes, you are.
Myself.
Sorry.
Okay.
Yeah, you froze for a moment.
All right, so I got cut off somewhere. I don't know where I got cut off, so I'm going to repeat what I was saying. Students are able to take register up to 21 credits of coursework per semester, which is covered by the tuition. They can take more than 21 credits. Sometimes, I believe sometimes they can get a waiver, and that credit is still covered in their tuition. But most times, if you want to take more than 21, you might end up paying for the extra credits. But that, I don't know any student who actually did that, to be honest. Every engineering student at RPI takes 3 free electives, excuse me. These courses can be anything. It could be other engineering courses. It could be School of Science courses. It could be arts courses, right? Maybe you want to do painting or you want to participate in the orchestra. So those credits could come from there. And every engineering student also takes 5 humanities and social science courses. These 5 courses are split into 2 of them must be from humanities, 2 of them must be from social sciences. Some of these has to be, at least one of these has to be communication intensive, which means that you need to have substantial amount of writing in that course, or communicating, verbal communications, for example, through presentations and so forth. We have basic engineering courses, which are not necessarily taught by the individual departments. We have a department called Core Engineering. It's a department with no students. Their only goal or mission is to provide the courses that all engineers commonly take. For example, statics, which is not called statics at RPI. It's called Introduction to Engineering Analysis. And then there's a course called Introduction to Engineering Design. There are some leadership courses, professional development 1, 2, and 3. 1 and 2 are taught by core engineering. Professional development 3 is a humanities and social science course. So all of these things put together, I guess what I'm trying to say is, you are not only learning about material science and engineering, if you're a material science and engineering major, you are getting all the other necessary components of how to be an engineer, how to be a manager and a leader, and how to communicate your ideas, communicate your findings, maybe testing tests, or communicate your research to people, raise money for a business idea that you have. All of these are actually covered in different courses. There are a lot of other programs that I recognize we don't really mention. Like, I've never mentioned some of these in any of my talks with undergraduates, but there are many other programs where it's like clubs or activities organized by faculty members sometimes, where they try to bring business and engineering together. So they have, for example, these engineering business competitions. You go through a 6-week course, and this is not an official course. It's not a credit course. It's like a workshop, 2 hours per week for 6 weeks. And you develop your idea. I mean, this is why you go through this course, actually. The course is about business and how do you make a business proposal and so forth. But you're an engineer. You develop your idea with the help of the faculty members in business school. And then you do a presentation as if you are pitching your idea to a group of investors. And at the end, they pick 1 or 2 and give you a financial award. And it's possible that if your idea is very good, these business faculty put you in touch with real investors that might actually finance your idea. So there are all kinds of other things going on at RPI that is not just about education per se. It's not just coursework. When do we decide our major? Ansu asked. Alex, when do they decide their major?
Don't worry, I've got this one. So typically, if you're looking to graduate in 4 years, we recommend that you declare your major by the end of your 3rd semester. So that's around December of your sophomore year. Some people do wait until the full kind of 2 years, so the end of their sophomore year to do it. Maybe if you have AP credits, for example, like we were talking about, IB credits, dual enrollment credits. But yeah, typically, if you want to stay on track and graduate in 4 years, we recommend end of your 3rd semester is a good time frame.
Thank you. Benjamin has an interesting question. He's asking us specifically, why do we love material science? And Ed said he loves material science because it combines cool science at the molecular and nano levels with useful engineering. That's a nice description. I will confess, when I was at your age, and I'm from Turkey, so the university that I attended did not have a standalone material science and engineering department. I ended up in mechanical engineering, but mechanical engineering actually had 6 tracks, and one of those was a materials track. So I ended up there because I liked the course content, and I have actually got to know the professors on the material side of mechanical engineering better. Did some work with one of them. And then when I decided to go to graduate school, I was still continuing initially into mechanical engineering, but then I met a professor who happened to be the most productive student of a chemistry Nobel laureate. And then sometimes you just have to be in the right place at the right time, I guess. And that took me to United States, to Akron, Ohio, where I studied polymer engineering and polymer science. So my relationship to material science and engineering is not like many other faculty members who might be coming from material science and engineering background with an undergraduate degree in material science and engineering background. I actually came through a very different route into materials. I ended up loving the theoretical part of polymers. I had not done any work in the lab with polymers. I actually did calculations, wrote a computer code in Fortran at the time, run my own calculations on my own, and I liked it. And I ended up at graduate school. You might find yourself in many different situations, and I tell my students, just keep your eyes open, keep your options open. It is possible that you know exactly what you want to do today, but you have no idea what tomorrow is going to bring to you. So if you're taking a course and you happen to love that course content, maybe that course content is telling you something, right? If you loved it, you were very successful, maybe that's the kind of discipline you want to follow. Many students know if they like material science or not when they take the 4-credit material science course. Approximately half of all majors in the School of Engineering take this course, and we do recruit students from that course at the end. Once students take that course, maybe we get 5 to 10 students on top of those who already came in declared as material science engineering students. Are there any computer softwares or programs that we should get familiar with when going into this major? I don't think so, but if you know anything, that's perfect. If you don't know anything, you will learn, right? You learn, and I found out that I learn best when I'm forced to do something and I need under pressure, then you learn. Robert asked, can I use my credits from Project Lead the Way at RPI? Alex?
Oh yeah, I just responded in the chat. Project Lead the Way credits do not transfer to RPI. Like we said before, we do accept 5s on the AP exams, 6s and 7s on the higher level IB exams, and we also accept dual enrollment credits for which you received credit that didn't count toward your high school degree.
Okay. Oh, we should talk about, I see some salary somewhere here. As I said at the beginning, we don't have a lot of undergraduate students, and there are approximately 60 material science and engineering departments within the United States of America. So there aren't a lot of material science and engineering students graduating per given year. And over the years, I've been at RPI since 2002. Almost all of our students either have jobs or are already going to decided and accepted into graduate schools by the time they are in the spring year of their senior year, spring semester of their senior year. Approximately, when was that? The last economic crash, I'm not talking about this one, the one in the late 2000s, when the markets crashed. 2008, yes. That year, we were graduating 24 students, and almost everybody else, especially biomedical engineers, and I'm not saying this to scare you from these disciplines, please don't get me wrong. But I have known a lot of students in mechanical engineering and biomedical engineering. These are very big departments in our school, and many of those students did not have jobs, could not have jobs. I have known personally many of them worked at in Troy for the next year or so at restaurants. Whereas the 24 undergraduates that we had, 23 of them had jobs already secured, and or graduate school, sorry. And one of them lost the job offer, was rescinded due to the economic crash. And that student was an American citizen. He was able to find a job like approximately 3 months later. And he actually stayed local. He went to a local company here. And then the 24th student was a foreign national. And that generally takes a little bit more time for them to find jobs anyways. But I know that she also secured a job within 6 months of her graduation. So generally speaking, material science engineering students, I mean, of course, unless you are a horrible student, you have a horrible GPA, right? That's not what you are coming to RPI for. Hopefully, you know that you still have to study. But if you do your job, get good credit, good grades, study for your courses, you will have a job at the end, or you will be able to go to even a better school for graduate studies once you are done at RPI. How many undergraduate students do you have throughout your engineering school? I don't know. How many, Alex?
Well, okay, so we have about 6,600 undergraduate students, and I would say roughly 45 to 50% of our students, if not more, are in the School of Engineering. So 50% of 6,600, around 3,300.
Okay, so as we said before, School of Engineering is the biggest school at RPI, so we have the majority of the students. I would say most of these students, though, are in mechanical, electrical, chemical, biomedical. I think those are the big departments at our school.
Aeronautical.
Aeronautical too? I didn't know that.
Yeah.
Wow, okay. All right. What should we do, Alex? I am done with the slides. We can entertain, obviously, more questions.
Yeah, I don't see any other questions. If anyone else has any questions, you're welcome to send them in. But if no one else has any questions and you all are finished with your presentation, we can absolutely close out of this presentation. If you're open to receiving questions from students, I see actually you already did. You listed your email addresses. So
yes.
Students, if you have questions that you don't want answered live, or you want to go a little bit more in depth, both of our wonderful faculty here are open to receiving those questions from you via email. So feel free to do that as well. And I'm still not seeing any other questions come in. So
okay,
I think we can close it out.
All right, perfect. I think that we'll call it.
Great. Thank you so much, both of you, for taking the time
to
talk to our students tonight. This has been wonderful. And students, of course, again, feel free to reach out with questions.
Absolutely.
Thank you. Thanks to all the students for taking the time to join us.
All right. Have a good night, everyone. Thank you.